There is a place on this planet, right now, tonight, where the pressure is so extreme that steel bends and bone dissolves, where the darkness has never once been broken by natural light, where creatures live that would come apart if you brought them to the surface, where sounds have been recorded that no scientist has been able to explain, and where the first thing James Cameron found when he landed at the deepest point on Earth was a plastic bag. This is the Mariana Trench, and we have barely begun to understand it. Chapter 1: The Last Blank Space. If you enjoy Earth at night and our slow journeys into the world's deepest mysteries, please take a moment to like this video and subscribe to the channel. We truly love when our community gathers in the comments to discuss what we explore together, react to each other, share what surprises you. It is one of the most special parts of what we do here. Now, let us begin. Tonight we are going somewhere that no satellite has ever clearly seen, somewhere no map has ever truly captured, a place on this very planet, in this very century, that remains one of the least explored locations in the entire solar system. Before this journey is over, you will hear about two men who chose to keep descending after their vessel cracked open 7 miles underwater. You will encounter a creature so perfectly adapted to impossible pressure that bringing it to the surface would cause its entire body to dissolve. You will hear sounds recorded from the deepest abyss that no scientist has ever been able to explain. And you will discover that the most remote and unreachable place on Earth was visited by a piece of human garbage long before any human being ever set foot there. This is the story of the Mariana Trench, the deepest place on Earth, and one of the last true unknowns remaining on the map. We live in an age that feels like total knowledge. Satellites photograph every street on every continent. We carry interactive maps of the entire planet in our pockets. We can look at the surface of Mars in higher resolution than we can observe our own neighborhood from orbit. Every mountain range has been charted. Every river has been named. Every forest has been catalogued from above. The puzzle, we are quietly told by the world around us, has been solved. It has not been solved. The ocean covers 71% of the surface of this planet. 71%. More than 2/3 of the world we live on is submerged beneath water. And of everything that lies beneath that water, the vast majority has never been directly observed by human eyes. Not seen, not photographed, not mapped with anything close to the precision we use to chart the land above the waterline. The seafloor maps you might find in a textbook or on a website are not what most people assume them to be. They are not detailed surveys built from direct observation. They are low-resolution estimates, assembled from satellite measurements of the faint gravitational distortions that large underwater features create on the ocean surface far above them. They look precise. They look complete. But the resolution of our best global seafloor maps is roughly 5 kilometers per pixel. Our maps of the surface of the Moon are more detailed than this. Our maps of Mars are more detailed. We know the shape of distant worlds better than we know the shape of the floor beneath our own oceans. And at the very deepest point of all of it sits the Mariana Trench. The Mariana Trench is a crescent-shaped scar in the floor of the Western Pacific Ocean, roughly 2,500 kilometers long and 70 kilometers wide at its broadest point. It lies east of the Mariana Islands, a chain of volcanic islands that is itself one of the products of the same forces that carved the trench into existence. The trench is not merely deep in the way that any ocean is deep. It is the deepest feature on the surface of this entire planet. At its lowest surveyed point, a specific location known as Challenger Deep, the ocean floor descends to approximately 10,935 meters below sea level. That is nearly 11 kilometers of water pressing down above you. That is deeper than Mount Everest is tall. If you placed the highest point on land into the deepest point of the ocean, the summit of Everest would still sit more than a mile beneath the waves. The trench was first measured in 1875 by HMS Challenger, a British Royal Navy survey vessel conducting what was then the first dedicated scientific expedition ever launched to study the world's oceans. The crew lowered a weighted rope over the side of the ship and measured the depth by how much line it took before the weight stopped descending. That number, 11 kilometers of rope, astonished the men who recorded it. They had no framework for understanding what it meant. They had found the bottom of the world, with a rope and a weight, from the deck of a sailing vessel. And they had no way of going there themselves. For most of the century and a half since that first measurement, nobody could. The physics of the deep ocean make the trench the most hostile environment on this planet. Pressure is the governing force of everything that happens there. It shapes what can live, what can descend, what can survive, and what will be destroyed. At the surface of the ocean, the weight of the atmosphere above us presses down at approximately 1 unit of atmospheric pressure. We are built for it. We have always lived inside it. We do not feel it at all. But for every 10 meters you descend beneath the ocean surface, you add another full atmosphere of pressure to whatever you carry with you. At 100 meters down, the pressure is 10 times what it is at the surface. At 1,000 meters, it is 100 times. At Challenger Deep, 11,000 meters below, the pressure exceeds 1,100 atmospheres. That is more than 16,000 pounds of force pressing against every single square inch of exposed surface area. Steel warps at these depths. Titanium deforms. Ordinary hollow structures implode in milliseconds. The chemistry of matter itself begins to behave differently. This is not a place that is difficult to reach because it is far away. The Mariana Trench is not distant in the way that deep space is distant. It sits on this planet, in this ocean. The surface of the water above it is accessible to anyone on a boat. The extreme inaccessibility of the trench is not a matter of distance. It is a matter of pressure. The trench does not turn you away. It does not keep you out by putting space between you and it. It simply crushes everything that arrives unprepared. Every meter of descent adds weight. Every 100 meters multiplies it. The deeper you go, the more the ocean presses inward against whatever you have brought with you, compressing it relentlessly toward failure. And yet, life has found a way to exist down there. Not just microbial traces clinging to sediment surfaces. Not just the sparse, slow remnants you might expect in a near-dead environment. The Mariana Trench hosts a functioning ecosystem, a food web with predators and prey, creatures with eyes that have never seen a single photon of natural light. Organisms so completely adapted to pressures that would destroy every familiar form of life that the pressure itself has become not their obstacle, but their home. The abyss does not merely tolerate them, it made them. We know this not because we have explored the trench fully. We know it because of a small number of extraordinary descents by a handful of humans and their machines, each of which lifted just one corner of a curtain that remains, by almost any honest measure, still largely closed. The ocean has a bottom. We have a name for it. We have measured it. We have, on a very small number of occasions, briefly visited it, and we understand almost nothing about what truly lives there. The map ends at the waterline. Below it, in the deepest places, it ends again. And what waits at the far end of that second ending is where we are going tonight, slowly, quietly, 1 kilometer at a time, past the last reach of sunlight, past the last trace of warmth, past the last familiar thing, all the way down to the bottom of the world, where the pressure is absolute and the dark is permanent, and something ancient has been waiting there for a very long time. Chapter 2. The Crack in the Dark. There is a moment in the history of human exploration that almost no one talks about. Not because it is obscure, but because the people who lived through it were so calm in describing it afterward that the world never quite registered how extraordinary it was. It happened on the 23rd of January 1960, 50 miles off the coast of Guam, in the Western Pacific Ocean. Two men climbed into a steel sphere barely large enough for both of them to sit upright and began to fall. Not toward the surface, away from it, down through the cold, darkening water toward the floor of the Mariana Trench. Their names were Jacques Piccard and Walsh, and before they reached the bottom, the vessel cracked. The bathyscaphe they were aboard was called the Trieste. It was an unusual machine by any standard. It was not a sleek submarine. It was closer in design to a hot air balloon than to anything most people would recognize as a seafaring vessel. A massive elongated float, 40 meters long, filled with aviation gasoline rather than air, because gasoline is less compressible than air under extreme pressure and provides buoyancy without the risk of implosion. Beneath this enormous float, suspended by a framework of steel, hung the part that mattered for the two men inside. A sphere, a single hollow sphere of forged steel, 5 inches thick in its walls, 79 inches across. Just large enough for two human beings to sit inside it, shoulder to shoulder, unable to fully stand or stretch their arms. The viewport of that sphere was a cone of plexiglass 6 inches thick at its outer face. The entire surface area of the outside of the sphere, every square inch of steel, would be carrying more than 16,000 pounds of force per square inch by the time they reached the bottom. The sphere was designed by Swiss engineer Auguste Piccard, Jacques' father, who had already taken a similar vessel to 7,000 meters in the 1950s. The mathematics of the design said it would hold. The engineering teams had calculated the tolerances. The steel had been inspected. The trench, as it would do again and again in the years that followed, did not care about the mathematics. The descent began at 8:13 in the morning. They fell at a rate of roughly 1 meter per second. For the first 1,000 meters, there was still a faint trace of light reaching them from above, a deep greenish blue that slowly shifted to indigo, then to something that was not quite any color at all. By 1,500 meters, the light was gone, not dimmed, gone. The world outside the viewport was absolute black. A cold, featureless, permanent dark that had existed since before human beings existed, and would exist long after everything that was happening inside that small steel sphere had been forgotten. They fell for nearly 5 hours. At approximately 9,000 meters, with the seafloor still more than 1,000 meters below them, there was a sound. It was not a groan. It was not a creak. A vessel under pressure groans constantly, settles, adjusts, makes the small sounds of stressed metal working against itself. Those sounds they had been hearing for hours. This was different. This was a single sharp crack, loud and clean and structural, that reverberated through the entire sphere like a hammer strike against the inside of a bell. The kind of sound that, in a pressurized environment 7 miles below the surface of the ocean, should produce only one response in the human body. The kind of sound that means something has broken. Piccard and Walsh looked at each other in the small red glow of the instrument lighting. Neither of them spoke immediately. They checked the pressure gauges. The internal pressure of the sphere was holding. The walls of the vessel had not failed. They checked the instruments for any sign of structural compromise. Nothing changed. The gauges read exactly what they had read before the sound. The sphere was intact. Whatever had made that noise was not the thing keeping them alive. They searched methodically for the source. After some time, they found it. An outer plexiglass observation window in the access tunnel between the float and the sphere, a non-structural component, had fractured under the accumulated pressure of the descent. The structural sphere itself was untouched. They were, by any engineering definition, safe. They chose to keep descending. This is the part of the story that deserves more than it is typically given. Two human beings, in the most isolated position any human had ever occupied, at a depth where no rescue was conceivable, where no other machine in the world could reach them, in total darkness, with a fresh crack in their vessel, and no certainty that the next crack would not be in the steel itself. They looked at the instruments, they looked at each other, and they decided that the bottom of the world was worth more than the safety of the surface. They had 20 minutes on the bottom, 20 minutes at the lowest point on the planet, with limited battery life, with a cracked outer window, and with the knowledge that the ascent would take as long as the descent. 20 minutes to observe what no human eye had ever observed. They noted the sediment, they noted the temperature, they noted the stillness. The complete, absolute geological stillness of a place that had been undisturbed since before our species existed. The floor of Challenger Deep does not move the way the surface world moves. It breathes on a timescale measured in thousands of years, not in seconds. To sit inside that sphere and look out at that pale, undisturbed sediment was, both men agreed, one of the strangest and most humbling experiences of their lives. They had traveled further from the surface world than any human being had ever traveled. And the world they found at the bottom was not violent or alien or dramatic. It was simply quiet, ancient, indifferent. Then something moved. In the illuminated water just above the silt, Piccard observed what he described as a flatfish, roughly a foot in length, pale, with two visible eyes. It appeared to look toward the light for a moment, then turned and swam slowly away into the darkness beyond the reach of the floodlights. A fish, a vertebrate, an animal with a skeleton and eyes and a nervous system. At 10,900 meters below the surface, where the pressure should make the existence of such a creature biologically impossible, where the chemistry of depth should prevent the calcification of bone, the function of swim bladders, the operation of any organ system that surface life depends on, both men were certain of what they saw. They reported it precisely: a flatfish, a sole or flounder type, eyes and fins and observable behavior. In the 60 years since that dive, no vertebrate fish has been photographed or filmed at that depth. Not during James Cameron's solo descent in 2012. Not during Victor Vescovo's record-breaking dive in 2019. Not by any of the robotic vehicles that have since visited the floor of Challenger Deep. The scientific consensus today leans toward the possibility that Piccard and Walsh, under extraordinary physical and psychological stress in the first moments of a historic landing, may have misidentified a pale holothurian, a sea cucumber with fin-like appendages, as a fish. Jacques Piccard maintained until his death in 2008 that he had seen a fish. Don Walsh, still living at the time of this writing, has never changed his account. The phantom of Challenger Deep has never been confirmed. It has never been disproven, and the floor of the deepest place on Earth has kept its answer to itself in the dark ever since. Chapter 3. The Voice of the Abyss. The deepest place on Earth is not quiet. This surprises almost everyone who first learns it. We imagine the abyss as a place of perfect silence, total stillness. The kind of deep, absolute quiet that we associate with darkness and remoteness and the absence of life. We picture it the way we picture deep space, empty, cold, mute. But when scientists first lowered titanium-cased hydrophones into the waters of the Mariana Trench in the 1990s, expecting at most a faint background hiss, their instruments were flooded with sound. Not a little sound. An overwhelming, continuous, layered landscape of acoustic information that they had not anticipated and were initially unprepared to interpret. The trench, it turned out, was one of the noisiest places in the Pacific Ocean, and some of what it was saying, even today, no one has been able to fully explain. The physics of why this is true begin with a phenomenon called the SOFAR channel. SOFAR stands for sound fixing and ranging. At a specific depth in the ocean, typically between 600 and 1200 meters, depending on location, a combination of water temperature, salinity, and pressure creates a horizontal layer where the speed of sound reaches its minimum value, sound waves naturally bend toward the zone of minimum speed, the same way light bends through a lens. This means that sounds produced at or near the SOFAR depth do not spread outward in all directions and fade. They are bent back toward the channel and trapped inside it. A sound made in this channel can travel for thousands of kilometers with almost no energy loss. A single underwater explosion detonated in the SOFAR channel has been detected by hydrophones on the opposite side of the planet. The Mariana Trench creates an extreme version of this effect. Its depth and geometry make it one of the most powerful natural acoustic collectors on Earth. Sounds that originate thousands of kilometers away funnel into the trench and are amplified. Sounds generated within the trench itself are trapped and carried outward across entire ocean basins. When scientists listened to what the trench was channeling, the inventory was astonishing. They heard the grinding of tectonic plates, the literal sound of the Pacific plate pushing beneath the Philippine plate at the rate of a few centimeters per year. Not a metaphor, not an abstraction. The actual acoustic signature of the Earth reshaping itself, transmitted through the rock and into the water, and carried up through the acoustic layers to the hydrophones listening above. They heard earthquakes from thousands of kilometers away, arriving as low, slow rolling thuds that built over minutes and then faded. They heard supertankers passing miles above the trench surface, their enormous propellers churning a constant deep hum that filtered down through the water column and entered the trench's acoustic record. They heard the barometric pressure of typhoons striking the surface, their energy transmitted downward in waves that the hydrophones registered as a slow, long-period pulse. And most beautifully, most surprisingly, they heard the songs of baleen whales. Single calls produced somewhere in the open Pacific, trapped in the deep sound channel and carried intact across thousands of kilometers of ocean to arrive at the trench floor as a ghostly, perfect, low-frequency murmur. The trench is a library. It collects the sounds of the entire Pacific world and holds them. Among the sounds collected since hydrophones were first deployed in the region, two stand apart from everything else. Not because they are the loudest, not because they traveled the furthest, but because no one, despite decades of analysis, has been able to fully explain what made them. The first became known to the public as the bloop. In 1997, the United States National Oceanic and Atmospheric Administration, monitoring the Pacific through its array of Cold War-era hydrophones, detected an extraordinarily powerful low-frequency sound. It was detected simultaneously by sensors more than 5,000 kilometers apart, meaning it had traveled across a vast stretch of ocean while remaining strong enough to trigger alarms. The sound rose rapidly in frequency over about 1 minute before fading. Its amplitude was off the charts. It was louder, by some measures, than the call of a blue whale, the largest animal on Earth. For years, it defied classification. Its biological frequency profile matched no known geological event. Its power suggested a source of enormous scale. And the scientific and popular imagination, quite reasonably given the circumstances, began to wonder whether something truly large and unknown was producing it from somewhere in the deep Pacific. The eventual explanation, confirmed by correlating the sound with satellite imagery and seismic data, was that the bloop was generated by the catastrophic fracturing and carving of a large Antarctic iceberg. The sound of millions of tons of ice breaking apart, transmitted through the water and focused by the deep sound channel into one of the most powerful acoustic events ever recorded. Not a creature, not a geological mystery, ice. But the Mariana Trench holds a stranger signal than the bloop. Between 2014 and 2015, researchers from Oregon State University, who had deployed hydrophones specifically to capture the ambient sounds of the trench, recorded a sequence of calls that stopped them completely. The calls became known as the Western Pacific Biotwang. Each call lasts just over 3 seconds and is composed of 5 distinct parts. It begins with a series of deep, resonant, low-frequency moans, each one dropping in pitch, like the groaning of a very large object under stress. Then, without any acoustic transition or preparation, the call leaps upward into a sudden, sharp, almost metallic twang. A sound so mechanically precise and so completely unlike the opening moans that the two parts seem to belong to entirely different sources. It does not match any known whale species. It does not match any documented geological or hydrological event. The leading scientific hypothesis is that it may represent a previously undocumented vocalization style of the dwarf minke whale, a species known to produce unusual metallic sounds in other ocean basins. But no minke has ever been recorded producing anything that sounds like the biotwang. No visual confirmation has been made. The call has no confirmed author. And then there are the sounds that are not officially recorded at all. Anecdotal reports from submarine crews and deep research vessel operators over the decades describe rhythmic metallic sounds from the deepest zones of the trench. Not the organic, biological range of a creature. Not the geological rumble of settling earth. Organized, metallic, rhythmic. The kind of sound that, if you heard it in an industrial building, you would assume was machinery. The leading mundane explanations are convincing enough on the surface. Old shipwrecks, of which many lie scattered across the Pacific floor at varying depths, slowly settling and shifting under pressure. Boulders and rocks in submarine canyons tumbling and striking each other, their impacts channeled and shaped by the trench acoustics into something that sounds more organized than it is. The groan of hydrothermal vent systems expanding and contracting with temperature fluctuations, these explanations are probably correct. The sounds probably have sources we understand or will come to understand. But in a place we have visited fewer than a dozen times, in a place that remains almost entirely unseen, in a place where the gap between what we know and what is actually there is still vast enough to hide entire ecosystems. The distance between a natural explanation and an unknown one is, for now, genuinely open. What we do know is this: the ocean is not a passive container for the sounds of the world above it. It is an active acoustic environment with its own physics and its own capacity for strangeness. The Mariana Trench is the deepest expression of that strangeness. Every sound that enters it is changed by it. Every sound that leaves it has been shaped by pressures and geometries that no surface world has any equivalent for. When we lower a hydrophone into that darkness and press record, we are listening to the Pacific Ocean itself, filtered through the most extreme acoustic lens on the planet. And what comes back is sometimes familiar, sometimes explainable, and sometimes something that sits at the edge of what we know and asks us, quietly, whether we have truly heard everything the deep has to say. Chapter 4. One Man in the Dark. On the 26th of March, 2012, 52 years after Jacques Piccard and Don Walsh made their descent, a single man climbed into a vessel roughly the size of a compact car and began to fall toward the floor of Challenger, deep alone. His name was James Cameron. The machine he had designed and built over 8 years of private engineering was called the Deep Sea Challenger. It looked nothing like the Trieste. Where the Trieste was massive and buoyant, a floating platform with a suspended passenger pod, the Deep Sea Challenger was a vertical torpedo, 24 feet long, lime green. Built to fall straight down at a rate of 500 feet per minute, nearly 3 times faster than the Trieste had descended half a century before. It was designed for speed because time at the bottom was the most precious resource. The faster the descent, the longer the science window. The pilot sphere at its center was 43 inches in diameter. Cameron could not fully extend his arms inside it. His knees were at his chest for the entire multi-hour journey. There was one viewport, a small dome of borosilicate glass rated to withstand the full pressure of Challenger Deep. The instruments were stacked around him in every direction. He had cameras mounted externally. He had scientific sampling equipment. He had a robotic arm. He had precisely the capabilities required for serious deep-sea research. And he had nobody to talk to in real time. The communication lag to the surface ship was significant. If something went wrong at depth, no voice on the other end of a radio could reach him in time to help. He was the single most isolated human being on the planet during those hours of descent. In the years since his dive, Cameron has spoken at length about the psychological quality of what he experienced on the way down and on the bottom. Not the fear, which he acknowledges was present but not dominant. Something larger, something that he has described in various interviews as a kind of profound philosophical solitude. A sense that he had been removed from the human world entirely and placed inside something that had been here long before humans existed and would be here long after the last of us was gone. The darkness outside the viewport was not the darkness of a room with the lights off. It was not even the darkness of being outdoors on a very dark night. It was the darkness of a place where darkness was the permanent, original state. A place where the very concept of light was an intrusion, not an absence. When the deep-sea Challenger reached the bottom, Cameron spent approximately 3 hours on the floor of Challenger Deep, the longest time any human had spent there. He used the robotic arm to collect sediment samples. He captured hours of high-definition footage. He documented organisms he could observe in the beam of the exterior lights. The samples and footage he brought back expanded the scientific record of the hadal zone meaningfully. And then his lights found something else. On the pale silt of the most remote and physically defended location on the planet, in a place that required the absolute outer limits of human engineering, private financing, and personal courage to reach, Cameron's cameras captured a plastic bag. Not a creature, not a mineral formation, not any of the 1,000 things that might belong at the bottom of the world. A plastic bag. The most common and disposable product of surface human civilization, drifting slowly along the floor of Challenger, deep in the faint current, undulating gently in the beam of the floodlight, as if it were alive. Let that image settle for a moment. We required 50 years of engineering advancement after Piccard and Walsh before we could send a single human being back to that floor. We required 8 years of custom engineering for the deep-sea Challenger specifically. We required one of the most technically accomplished and financially resourced private individuals alive. And when that person arrived, our garbage was already there. Our garbage did not need funding. It did not need engineering. It did not need courage. It simply fell, slowly, over weeks or months, down through 11 kilometers of water. And it arrived at the most inaccessible place on Earth without any effort at all. The plastic bag was not an anomaly. Research published in the years following Cameron's dive confirmed that the Mariana Trench is, in fact, a collector of surface debris. The geometry of the trench, a long, deep V carved into the ocean floor, concentrates, rather than disperses, what falls into it. Particles that drift down through the water column from the surface world are funneled toward the deepest point. Scientists studying sediment samples from Challenger Deep have found microplastic particles, fragments of synthetic fibers too small to see with the naked eye, in every single sample they have tested, not occasionally. Every sample, the bottom of the world is contaminated from edge to center. Victor Vescovo encountered similar evidence when he made his own dive in 2019, reaching 10,928 meters and setting the record for the deepest crewed descent in history. His dive was part of the 5 Deeps expedition, a privately funded mission to reach the deepest point of all 5 of Earth's oceans. He described his time on the bottom of Challenger Deep in terms that echoed Cameron's. The solitude, the geological weight of the place, the sense of inhabiting a world that operated on entirely different timescales than the one above. He also found a plastic bag and a sweet wrapper. The pattern across multiple crewed dives to Challenger Deep has been consistent. Human waste arrives before the humans who send it, not as a dramatic event, not as something anyone planned or noticed or grieved at the time it happened, but quietly, incrementally, particle by particle, The surface world has been raining down on the deepest floor for as long as we have been producing the materials that make up that rain. The plastic era began roughly in the 1950s. The ocean floor has been receiving its product ever since. Decades of slow, continuous, invisible delivery, long before any submersible ever switched on its lights down there. There is a philosophical dimension to this discovery that sits underneath the logistical one. The question it asks is not simply about pollution, though the pollution is real and serious, and we will return to it. The question it asks is about the nature of remoteness itself. We have spent decades treating depth as a form of protection, the deepest ocean as a place beyond our reach, beyond our influence, beyond the range of our casual destruction. The plastic bag in Challenger Deep is the definitive answer to that assumption. There is no depth at which we have not already arrived. There is no floor too far below us for our discards to reach. The concept of the pristine deep is not a hope deferred. It is a hope that has already been answered, clearly, by a piece of plastic drifting through the most remote darkness on this planet. Cameron ascended after 3 hours on the bottom. The buoyancy system released its iron ballast weights, and the vessel began to rise. The pale silt of Challenger Deep receded below him. The absolute dark closed back around the tiny point of warmth and light that he represented, and the floor of the trench went back to what it had been for the vast majority of its existence. Dark, still, patient, holding its secrets and our garbage in equal, indifferent silence. That silence is not empty. It never was. In the chapters ahead, we will begin to understand what actually lives inside it, what has spent millions of years solving the same impossible problem, and what the deepest ecosystem on Earth looks like when you finally turn the light on. Chapter 5. The Ghost Predator. When scientists think about apex predators, they tend to think about size. The great white shark, the orca, the lion, the creatures that sit at the top of their food chains are almost universally large, powerful, physically imposing animals. They have evolved their dominance through some combination of speed, strength, sensory acuity, and raw physical mass. The world imagines the apex predator of the deepest ocean in similar terms. Something enormous, something armored, something that looks the way the pressure of that world feels. A creature built like a siege weapon, designed to survive the crushing dark. The actual apex predator of the deepest place on Earth is about the size of a large banana. It has no scales. Its skin is translucent pink, thin enough that you can see the silhouette of its organs working inside. Its skeleton is not hardened bone, but flexible cartilage. It has no visible armor, no spine, no threatening physical features of any kind. It looks, if anything, like something fragile that has wandered into a place where it does not belong, like prey that has made a wrong turn. It is called the Mariana snailfish. Its scientific name is Pseudoliparis swire. It is roughly 28 centimeters long, and it is the most successful vertebrate animal at the greatest depth on Earth. To understand how this is possible, you first need to understand the environment it has conquered. Below 6,000 meters, the ocean floor belongs to a zone that scientists have given its own separate classification. Not merely a deeper version of the abyssal zone, the cold, dark plain that covers much of the ocean floor between 4,000 and 6,000 meters. This is something else entirely. It is called the hadal zone, a name derived from Hades, the Greek deity of the underworld. The name is fitting in every sense. The hadal zone encompasses the deepest ocean trenches on Earth. It is defined not simply by depth and darkness, but by what pressure does to chemistry at this scale. At hadal depths, pressure stops being purely a mechanical force. It becomes a biochemical one. It attacks the molecular machinery of life at the most fundamental level. Cell membranes, which in shallow water organisms are held in a stable fluid state by their lipid structure, are compressed under hadal pressure into a rigid, almost crystalline configuration that prevents them from functioning. Proteins, which need to fold into precise three-dimensional shapes to perform their enzymatic roles, are forced by the pressure into misfolded configurations that render them useless. The basic engine of metabolism, as we understand it from any surface life form, simply stops working at these depths. Cells cannot exchange materials across their membranes. Enzymes cannot catalyze the reactions that produce energy. Life, as we know it from every living thing we see around us every day, cannot operate here. And yet the snailfish operates here, dominantly, in large numbers. It has been photographed in aggregations of dozens of individuals, swarming over bait traps, moving quickly and purposefully through water at a depth where most biology would immediately die. The key to its survival is a molecule called trimethylamine oxide, commonly abbreviated as TMAO. TMAO is what scientists call a piezolite, a pressure-counteracting compound. It works by physically interacting with the proteins and membranes of the snailfish's body, preventing the misfolding and rigidification that extreme pressure would otherwise cause. It keeps proteins properly folded. It keeps membranes fluid. It is, in the most direct sense, the molecular reason the snailfish exists where it does. What makes this remarkable is not just that the snailfish has this molecule. Many marine animals produce TMAO in small amounts. What makes the snailfish remarkable is the concentration. As snailfish species are found at increasing depths, their TMAO concentrations increase proportionally and measurably. The molecule is being actively regulated as a function of the depth at which the animal lives. At the extreme depths of the Mariana Trench, the concentration of TMAO in snailfish tissue is the highest ever recorded in any vertebrate animal on Earth. The snailfish is not just tolerating the pressure, it is chemically saturated with the compound that counteracts it. Its entire internal biochemistry has been retuned around the pressure of the abyss. There is a consequence to this adaptation that is among the strangest facts in deep-sea biology. Bring a Mariana snailfish to the surface, and it will not survive in the way that a deep-sea fish in older stories might be depicted surviving. It will not explode outward from the decompression. That dramatic image, which is sometimes used to describe deep-sea fish, is a product of expanded swim bladders in fish that have them. The snailfish has no swim bladder. It does not experience the outward pressure release in that way. What it experiences is almost the opposite. Without the enormous pressure that its entire biochemistry has been calibrated to function under, the TMAO that holds its proteins together loses its purpose. The proteins and membranes that were in equilibrium with 16,000 pounds per square inch of external pressure suddenly have nothing pushing against them. The snailfish does not explode, it dissolves. The carefully maintained gel of its body, every cell membrane, and every protein structure loses cohesion. It reduces to a soft, formless slurry. The pressure was not its obstacle. The pressure was its life support. Without it, the snailfish simply comes apart. This creates a haunting symmetry between the snailfish and the humans who study it. We cannot go down to where it lives without being crushed by the pressure that sustains it. It cannot come up to where we live without being destroyed by the absence of that same pressure. We are mirror images, trapped on opposite ends of the same force, neither able to enter the other's world. The snailfish is the apex predator of the hadal zone, because nothing else has solved the pressure problem as thoroughly as it has. The amphipods it feeds on are abundant. The sediment is full of organic material it can access. It has no natural predators at this depth because nothing large enough to threaten it can function at these pressures. It did not become dominant through strength or speed in the conventional sense. It became dominant by going somewhere that everything else was excluded from. It built its kingdom at the bottom of the world by being the thing most willing to become part of the darkness. The snailfish was first confirmed as the deepest living fish on record in 2014 when researchers from the University of Aberdeen captured footage of it at 8,143 meters in the Mariana Trench. That record was subsequently extended. In 2017, footage emerged of snailfish at 8,178 meters. Each new depth record confirmed not just the animal's presence, but its apparent ease. It was not struggling at these depths, it was feeding, competing with others of its species for bait, moving with the casual confidence of an animal, entirely in its element. In 2023, a specimen was filmed at 8,336 meters, the deepest fish sighting ever recorded, pushing the known limits of vertebrate life further than any previous observation had reached. What the snailfish represents, stripped of the romance, is a simple and elegant biological truth. Evolution does not require comfortable conditions. It requires time and pressure. Given enough of both, life will find a way to turn even the most hostile environment into a home. The snailfish did not adapt to the trench despite the pressure. It adapted because of it. The pressure was the selection force that drove every solution its lineage eventually discovered. The trench made the snailfish exactly what it is. And the snailfish, in return, became the living proof that the bottom of the world is not empty. Life arrived there a very long time ago, and it has been thriving ever since, in the cold and the dark and the quiet, far beyond the reach of anything we thought we understood about what biology was capable of. Chapter 6. The Creatures of Glass. There are no hiding places in the deep ocean, on land, or in the shallow coastal seas. A creature that wants to avoid being eaten has options. It can press itself into a crevice in a rock. It can bury itself in sand. It can climb a tree or find a cave or lose itself in the dense architecture of a coral reef. The world of shallow life is structured. It has texture. It has shadows and corners and refuges. The deep ocean has none of these things. Below the range of light, in the open water column of the midnight zone and the abyssal depths, the environment is featureless in every direction. Not just ahead and behind and to the sides, but above and below. There is no floor to press against in the open column. There is no ceiling. There is nothing at all except cold, dark water stretching away in every direction into an equal and undifferentiated nothing. In this environment, the most effective camouflage is not a pattern or a color. It is the absence of a body to see. Evolution has discovered this solution independently in dozens of different lineages of deep-sea organisms. Animals from completely unrelated branches of the tree of life have converged, through millions of years of separate pressure, on the same answer. If nothing about you can be perceived, nothing about you can be targeted. The strategy is not to hide behind something. It is to become transparent. To let the eye, or whatever passes for an eye in the deep, pass through you as if you were not there at all. The telescope octopus is one of the most disorienting examples of this strategy in the entire ocean. Its scientific name is Amphitretus pelagicus. It is found in tropical and subtropical ocean waters at depths between 200 and 2,000 meters. Its body is almost entirely absent from a visual perspective. What exists is a very thin, nearly invisible membrane of tissue, a ghost of a body that scatters almost no light. Within that near-invisible form, the only clearly visible structures are its digestive organs, which appear as a faint dark smudge in the center of nothing, and its eyes, two enormous, elongated, tubular eyes, each one set on a stalk and capable of rotating independently, designed to swivel upward and scan for the dark silhouettes of prey moving against the slightly less dark water above. The telescope octopus does not hunt by seeing in the conventional sense. It hunts by watching for shadows. Everything about its body that could create a shadow has been reduced to almost nothing. It has become a pair of eyes floating in the dark, waiting. The glass squid takes a different approach to the same problem. Most glass squid species of the family Cranchidae are, as their name suggests, largely transparent. The body, called the mantle, is a clear balloon of tissue filled with fluid. The internal organs are visible through it. Under normal light conditions, a glass squid at depth is nearly undetectable to anything looking in its direction. But the glass squid has two structures that cannot be made transparent. Its eyes are large and opaque, and its digestive gland, a metabolically essential organ, is a dark, pigmented mass that sits within the otherwise clear body. These two structures cast shadows when illuminated by any light source from above, including the faint, diffuse, downwelling light from the surface that penetrates even into the upper reaches of the midnight zone. A shadow in the deep ocean is not an inconvenience. It is a death sentence. A shadow says, something is here, something with mass and structure, something worth investigating. The glass squid solves this with a trick so elegant it is almost unbelievable. Along the underside of its opaque organs, it grows rows of bioluminescent photophores, light-producing organs. These photophores produce a precisely calibrated glow that exactly matches the intensity and color of the faint downwelling light coming from the surface above. By projecting light downward from its own opaque structures, the glass squid erases its own shadow. To anything looking up at it from below, the darkness created by its opaque organs is cancelled out by the light it produces. It becomes, in effect, invisible. Not invisible by being absent, invisible by generating exactly the light needed to fill the gap its own presence creates. It is one of the most sophisticated passive camouflage systems in the natural world, built not from physical concealment, but from a precise manipulation of light that the squid cannot see itself producing. Then there is the dragonfish. The stoplight loose-jaw dragonfish, known scientifically as Malacosteus niger, is a predator of the mesopelagic and bathypelagic zones, found at depths between 200 and 1,000 meters. It is not a large animal. It is typically around 20 centimeters long, slender and dark, with a jaw structure that hangs open beneath a disproportionately large head. The jaw cannot be fully closed against the body. It hinges outward, allowing the dragonfish to engulf prey items that are nearly as large as itself. But its jaw is not what makes it extraordinary. Almost every creature in the deep ocean has evolved to perceive only blue light. Blue is the only wavelength of visible light that penetrates in any meaningful quantity from the surface into the deep. In a world defined by the absence of red, orange, and much of the green spectrum, no creature has any evolutionary reason to develop sensitivity to red wavelengths. Red light in the deep ocean does not exist. There is nothing to see it with and nothing to produce it. To the deep ocean, red might as well not be part of the visible spectrum at all. The dragonfish knows this, and it has exploited it completely. The dragonfish is one of only a handful of creatures on Earth that has independently evolved both the ability to produce and the ability to perceive far red light. It has a specialized photophore behind each eye that produces a beam of red light pointing forward into the water ahead of it, and it has modified photoreceptors in its eyes that detect that same red wavelength reflected back from whatever the beam encounters. It is carrying a biological lantern that only it can see. Any prey animal that drifts into the beam of the dragonfish's red spotlight is illuminated in a frequency it has never needed to evolve any sensitivity to. It cannot see the light. It cannot detect the predator watching it. It continues doing whatever it was doing, entirely unaware that in a frequency invisible to it, it is fully lit, fully visible, and fully targeted. The dragonfish watches it move in the private wavelength, and then the jaw hinges open. In the deep ocean, where every metabolic cost is precious and every hunting strategy must be efficient to survive, the dragonfish has achieved something close to a perfect asymmetry. It sees without being seen. It hunts in a dimension its prey does not know exists. There is a broader principle at work across all of these animals. In the deep ocean, the usual rules of predation and evasion have been rewritten by the fundamental fact of darkness. On land, or in the sunlit shallows, every creature is bathed in the same ambient light. Everyone can potentially see and be seen on roughly equal terms. In the deep ocean, light itself has become a resource. Who produces it, who perceives it, and which wavelengths each participant in the ecosystem can and cannot detect has become the central evolutionary contest. Bioluminescence is estimated to have evolved independently in the ocean more than 40 separate times across entirely unrelated lineages. It is arguably the most widespread form of biological communication on the planet, if measured by the number of individual organisms that use it. In the deep ocean, the only light that exists is the light that living things make themselves. And every creature present is either producing it, responding to it, hiding from it, or turning its absence into a weapon. The visual world of the abyss is not simply dark. It is a complex, shifting landscape of biological light played out in near total silence, in service of the most ancient contest in the history of life. Chapter 7. How the world carved itself. The Mariana Trench did not always exist. There was a time, deep in the geological past, when the Western Pacific Ocean floor was simply that, a floor. A relatively flat plain of basaltic rock sitting beneath kilometers of ocean, old and cold and dense, but not extraordinary. Not a trench, not a record, not the deepest place on a planet. And then, two things collided. The story of how the trench was made is, in one sense, a story about two enormous slabs of the Earth's outer layer meeting at the wrong angle over an inconceivably long period of time. But in another sense, it is a story about how the planet continuously rebuilds itself. How material that formed at one location in the Earth's crust eventually returns to the interior to be melted and reformed and sent back to the surface in a new form, in a new place, millions of years later. The trench is not a wound in the Earth, it is a recycling process, the most powerful and fundamental geological cycle on the planet, expressed at its most extreme. The Western Pacific Ocean floor is dominated by the Pacific Plate, one of the largest tectonic plates on Earth. The Pacific Plate formed at a mid-ocean ridge, a spreading center where magma rises from the mantle, pushes through the ocean crust, and solidifies into new rock. As new rock forms at the spreading center, the older rock is pushed outward across the ocean floor. The Pacific Plate has been doing this for a very long time. It is old rock. And old oceanic rock, unlike old continental rock, has a specific and consequential property. As it cools over millions of years, it becomes denser than the hot mantle rock beneath it. This density is what creates the trench. To the west of the Pacific Plate sits the Philippine Plate, a smaller, younger, slightly less dense piece of crust. Where the two plates meet, the physics are simple and inevitable. The older, denser Pacific Plate cannot ride over the younger plate. It bends, it curves downward, and it begins to slide beneath the Philippine Plate in a process called subduction. As the Pacific Plate descends into the mantle, it drags the ocean floor down with it. The surface expression of this downward drag is the trench. The floor of the Mariana Trench is where the Pacific Plate begins its long journey back into the mantle, bending under its own weight, pulled down by the density accumulated over 180 million years of cooling. The plates move at roughly the same rate that your fingernails grow, a few centimeters per year. This sounds trivially slow, but over the timescales that geology operates on, it is not slow at all. The Mariana Trench has been deepening at this rate for tens of millions of years. The total displacement of rock involved is staggering, and it is happening right now. At this moment, the Pacific Plate is moving. It is bending downward beneath the Philippine Plate. The trench is not a relic of a geological event that ended long ago. It is an ongoing event, an active, living geological process that has not stopped and will not stop for millions of years to come. The subduction zone that produces the trench is also one of the most seismically active regions on Earth. As the Pacific Plate descends, it does not slide smoothly. It is a cold, rigid slab of rock being forced down into a hot, less rigid environment. The descending plate sticks and catches on the plate above it. Stress builds along the contact zone between them. Sometimes that stress releases gradually, in small, frequent tremors that the instruments detect but that no surface observer would ever feel. And sometimes it releases all at once. When a locked section of the subduction zone finally ruptures, the energy release is enormous. The upper plate, which has been dragged slightly downward by the sticking slab beneath it, snaps back upward. In seconds, a section of ocean floor the size of a small country lurches upward by meters. The water column above it is displaced in an instant, and that displaced water has nowhere to go except outward in all directions, a tsunami. The connection between the Mariana subduction zone and tsunamis is not abstract. The mechanism that produces the trench is the same mechanism that has generated some of the most catastrophic ocean events in recorded history. The 2011 Tohoku earthquake off the coast of Japan, which triggered a tsunami that killed nearly 20,000 people and caused the Fukushima nuclear disaster, originated from a subduction zone structurally identical to the one beneath the Mariana Trench. The plates involved were different, but the physics were the same. A dense oceanic plate descending beneath a lighter one. Stress accumulating over decades. A sudden catastrophic release. A wall of water crossing the ocean at the speed of a commercial aircraft. There is another dimension to the seismicity of the Mariana subduction zone that puzzles geologists even now. The earthquakes produced there are not limited to the upper crust where subduction happens. Deep in the descending Pacific Plate, at depths of 300 to 700 kilometers below the surface, earthquakes are regularly recorded. This should not be possible. At those depths, the temperature and pressure are so extreme that rock should not behave in a brittle way at all. It should flow. It should deform plastically, the way hot glass deforms when you press it. Brittle fracture, the process that produces earthquakes, requires cold, rigid rock. At 700 kilometers down, the rock is neither cold nor rigid, and yet it breaks. The leading hypothesis involves water. The descending Pacific Plate carries with it the hydrated minerals of the ocean floor, compounds that have chemically bound water molecules into their crystal structure over millions of years of contact with the ocean above. As the plate descends and heats up, these minerals release their water. That water, at extreme depth, alters the mechanical behavior of the surrounding rock in ways that may enable brittle fracture where it otherwise could not occur. The plate may be, in effect, lubricating its own failure, releasing the fluid that allows it to break at depths where breaking should be impossible. These deep earthquakes are typically not felt at the surface with any great intensity. They are too far down, too well insulated by the rock above them, but they are recorded. They tell us that the subducting slab is not passive. It is active, stressed, and periodically fracturing all the way down to depths that our models of rock mechanics still struggle to account for. What descends into the mantle does not simply vanish. The subducting Pacific Plate carries with it everything that has accumulated on its surface over 180 million years of ocean floor existence. Sediment, marine snow, the compressed remains of countless generations of ocean life, the minerals that living things built their shells and bones from. All of it is carried down with the plate. Some of it is scraped off against the overriding Philippine plate as the two meet, piling up in a wedge of compressed material at the leading edge of the trench. Some of it is dragged further down into the mantle, where it is eventually melted, mixed back into the rock of the interior, and returned millions of years later as new magma rising through the crust elsewhere. The Mariana Islands themselves are one product of this return. The volcanoes that form the island chain were built from magma generated partly by the melting of the subducting Pacific Plate deep in the mantle. The water carried down by that plate lowers the melting point of the surrounding mantle rock, producing magma that rises through the crust and erupts at the surface. The islands standing above the trench to the west are, in a real sense, made partly from the floor of the trench itself. Rock that was once ocean floor, pulled down into the deep earth, melted and sent back upward in a new form, in a new place. The planet recycles everything. The trench is where that recycling begins. And it has been doing so right now, at this moment, as quietly and as inevitably as it has for tens of millions of years, regardless of whether anything alive on the surface notices. Chapter 8. Fire and Champagne. Deep within the Mariana Trench system, in a region of the seafloor far from Challenger Deep, but still within the broader volcanic arc that the subduction zone has created, there is a place where something emerges from the rock that should not be there. Not black smoke, not the red glow of lava, something quieter and stranger than either of those things. A slow, steady, pearlescent stream of bubbles rising from a crack in the seafloor, shimmering, gentle, almost beautiful, ascending through the dark water in a column that catches the light of a submersible's flood lamp and refracts it into something that looks, improbably, like the inside of a glass of champagne. The scientists who discovered it named it exactly that, the champagne vent. What those bubbles contain is not gas. At the depth and pressure of the champagne vent, the substance streaming from the seafloor is liquid carbon dioxide. On the surface of the Earth, carbon dioxide is the invisible gas we exhale with every breath, the compound that fizzes in carbonated drinks and that fills the atmosphere in trace quantities responsible for the planet's heat balance. To exist as a liquid, carbon dioxide requires either very high pressure or very low temperature, or both simultaneously. The natural surface world almost never provides these conditions in combination. At the champagne vent, the crushing pressure of the deep ocean and the relatively cool temperatures of the seafloor provide exactly the right combination, producing a natural phenomenon that chemists have to build expensive laboratory equipment to replicate. The liquid carbon dioxide seeping from the rock is denser than the surrounding seawater. It pools. It forms small shimmering lakes in depressions on the seafloor. It rises in lazy columns of droplets rather than the sharp upward jets of a gas vent. It is a window into a chemistry that operates by rules so different from the surface world that standing observers describe it as watching a planet that is not quite Earth. The champagne vent represents the quieter and stranger end of a spectrum of hydrothermal activity within the Mariana system. At the dramatic opposite end of that spectrum are the black smokers. Black smokers are among the most visually spectacular geological phenomena on the planet. They begin with a crack. Seawater seeps through fractures in the ocean crust and begins to descend toward the underlying magma, driven by the pressure differential and by gravity. As it travels downward through the rock, it is heated. Not gradually, with extreme, rapid intensity. The water reaches temperatures above 400 degrees Celsius, hot enough to melt lead, hot enough to vaporize on the surface in an instant. But at the pressures found kilometers below the ocean's surface, water cannot boil. It becomes a superheated liquid under pressure, a state that does not exist in the surface world. And in this state it dissolves the surrounding rock, sulfur, iron, zinc, copper, manganese. The chemistry of the ocean crust dissolves into the superheated fluid as it travels through it, producing a concentrated mineral-laden solution of almost industrial intensity. When this superheated fluid reaches a point where it can exit back through the seafloor, it blasts upward through a chimney structure formed from previously precipitated minerals. It hits the near-freezing ambient water of the deep ocean at the vent opening. The temperature differential is extraordinary, sometimes more than 400 degrees across a distance of centimeters. In that collision, every dissolved mineral in the fluid precipitates instantly out of solution, not slowly, instantly. As fine, dark particles that billow upward from the vent in dense, opaque clouds, the black smoke that gives the structures their name. Over years and decades, The precipitating minerals build up around the vent, opening into chimney structures that can reach heights of 60 meters or more. Towers of sulfide minerals growing from the seafloor, constantly venting superheated black fluid from their tops, surrounded at their bases by the only ecosystem on Earth that does not depend on the sun. When the first robotic submersibles reached the hydrothermal vents of the Pacific in the late 1970s, the scientists operating them expected to find sterility. The deep sea had long been understood as a food desert, dependent entirely on the slow rain of organic material from the surface above. Vent sites, where the temperature and chemistry were extreme, even by deep-sea standards, seemed like the last place any complex life would establish itself. What the cameras found instead stopped the scientists watching in silence. Tube worms, pale, ghostly, enormous, growing in dense clusters around the base of the vents, reaching lengths of 2 meters or more, with no mouth, no stomach, and no digestive system of any kind. They were drawing all of their nutrition from bacteria living within a specialized organ inside their body, bacteria that oxidized the hydrogen sulfide pouring from the vent and used the energy of that chemical reaction to fix carbon, to build organic molecules from scratch, using chemistry instead of sunlight as their energy source, chemosynthesis. A biological process that had been theoretically understood but never observed operating at this scale, supporting this density of life in this complete independence from the sun. Around the tube worms were crabs, white and slow, moving over the mineral surface with the deliberate patience of animals that have never seen light and have no use for speed. Shrimp clustering at the edges of the vent openings in such density they formed living carpets, their compound eyes reduced or absent. Fish circling slowly in the warm water above the vents, feeding on the invertebrates below. An entire ecosystem, complete from primary producer to apex consumer, running entirely on the chemical energy coming from the planet's interior. The implications of this discovery extended far beyond biology. For the entire history of science up to that point, the sun had been considered the universal energy source for life on Earth. Every food chain, no matter how indirect, traced back eventually to photosynthesis, to the sun. The discovery of chemosynthetic vent communities broke that assumption permanently. The sun, it turned out, was not required. Life could run on chemistry alone, on the energy of the planet itself. In a single dive, the boundary of where life was considered possible expanded to include every dark, cold, pressurized ocean in the solar system, and the questions that expansion raised have not stopped growing since. The hydrothermal vent ecosystems of the Mariana system are not uniform. Each vent field has its own chemistry, its own temperature profile, its own community of organisms. Some vent communities are dominated by tube worms, others by dense mussel beds that host chemosynthetic bacteria in their gill tissue, some by ghostly pale octopus that prey on the invertebrates clustered at the warm edges. The variability between vent communities, separated by only a few kilometers of seafloor, can be as great as the variability between two entirely different ecosystems on the surface world. Each vent is, in effect, its own island, a warm, chemically rich oasis in the cold, dark desert of the deep seafloor, connected to other vent communities only by the slow dispersal of larvae through the water column, isolated enough that each community can develop along its own evolutionary trajectory. Species found at one vent in the Mariana system may be found nowhere else on Earth. These ecosystems are also, in geological terms, temporary. A hydrothermal vent is powered by the heat of the magma below it. When the magma chamber beneath a vent site cools or shifts, the vent dies. The flow of superheated fluid stops. The temperature drops to ambient. Without the chemical energy source, the primary producers die, and the entire ecosystem collapses in a matter of years. What was a dense, thriving community of life becomes a silent field of mineral chimneys, cooling slowly in the dark. The organisms that built their lives around the vent are gone. the record of their existence preserved only in the mineral deposits they helped build, and in the sediment that slowly buries everything the trench receives. New vents open elsewhere. New communities seed themselves from the larvae that have been drifting through the water column. The cycle continues, but each individual vent community is transient. A brief moment of warmth and chemistry and life in the long, cold darkness of the ocean floor, which makes the question of what happens when we begin to mine them not merely a practical question, but a philosophical one. Chapter 9. Where life began. For most of the history of biology, the story of life's origin had a particular quality to it. It was a story of warmth and light. Charles Darwin, in a letter written in 1871, speculated about what he called a warm little pond. A small, shallow body of water, warmed by the sun, rich in simple chemical compounds, struck at intervals by lightning, in which the first self-replicating molecules might have assembled by accident and begun the chain of events that eventually produced every living thing on this planet. The image is gentle, almost pastoral. It places the origin of life in a setting that humans find comfortable and recognizable. Warm, bright, accessible. The discovery of hydrothermal vents and the chemosynthetic ecosystems thriving around them in total darkness under crushing pressure did not merely add a new location to the list of places where life could exist. It raised a question that biology had not previously needed to ask. What if life did not begin in Darwin's warm little pond? What if it began in the opposite of a warm little pond? What if it began in the dark, at the bottom of a cold sea, in the superheated crack of an ocean floor? The hydrothermal vent hypothesis for the origin of life is not a fringe idea. It is one of the most seriously considered and most actively researched proposals in the field of abiogenesis, the study of how life first arose from non-living chemistry. It was developed most influentially by the British biochemist Michael Russell in the 1990s and has been refined and expanded by researchers around the world in the decades since. The core argument is this: a hydrothermal vent is not just a source of heat and chemicals. It is a source of something more specific and more chemically powerful. It is a source of a steep gradient between two chemically different environments. The superheated, mineral-rich, alkaline fluid rising from the rock on one side, the cold, slightly acidic, relatively mineral-poor ocean water on the other. Where these two fluids meet, in the porous mineral structure of the vent chimney, there is an extraordinary concentration of chemical energy, the kind of energy that drives reactions, the kind that could force simple molecules together into more complex ones, the kind that could, given enough time, push chemistry toward the first fragile steps of self-replication. But there is something more specific still. The mineral structures of hydrothermal vent chimneys are permeated with tiny, interconnected pores. These pores, formed from iron and sulfur compounds, are roughly the size of a biological cell, and iron sulfide, the primary mineral of these pore walls, is catalytically active. It can facilitate chemical reactions. In the 1980s and 90s, when researchers began to look carefully at the chemistry of iron sulfide under hydrothermal conditions, they found that it could catalyze the synthesis of some of the most fundamental molecules in biology, including the building blocks of the molecules we now consider the signature of life. The proposal is that these tiny pores in the vent chimney walls acted as the first protocells, not cells with membranes, but enclosed, chemically active spaces where simple molecules could be concentrated and forced to react with each other, generation after generation of chemical accident and selection, until something emerged that could copy itself. And once self-replication exists, even the most primitive and error-prone kind, the rest of evolution becomes possible. Everything that has ever lived, every organism that has ever eaten or reproduced or adapted or died, would be the descendants of a chemistry that began in a crack in the ocean floor, in darkness, under pressure. Powered not by the sun but by the heat of the planet itself, This is a profoundly different origin story from the warm little pond, and it carries implications that extend far beyond Earth. The adaptations that deep-sea life has evolved to survive hadal pressures have also revealed something unexpected about human medicine. The same molecular problem that the snailfish solves with TMAO, the misfolding of proteins under physical stress, is also implicated in several of the most devastating neurological diseases that affect human beings. In Alzheimer's disease, in Parkinson's disease, in a number of related conditions, the core biological event is the misfolding of specific proteins in neural tissue. Proteins that adopt the wrong three-dimensional shape and, as a result, clump together in ways that damage and eventually destroy the neurons that produce them. The snailfish has been solving a version of this problem for millions of years. Its TMAO-based system for keeping proteins properly folded under extreme pressure is, at a molecular level, addressing the same type of protein instability that underlies these diseases. Researchers studying the biochemistry of deep-sea organisms have identified several molecular pathways and compounds in hadal species that could, potentially, offer insights into how to prevent or reverse protein misfolding in human cells. The most alien creature on the most remote floor of the most extreme environment on the planet may carry, in its biochemistry, a partial answer to diseases that affect tens of millions of people. The hadal genome, the genetic toolkit of organisms adapted specifically to hadal depths, has also revealed something surprising about the history of life on Earth. Some of the genes found in deep-sea hadal organisms have no clear analogues in any shallow water relative. They are not simply modified versions of genes from less extreme environments. They appear to be genuinely novel, with no obvious evolutionary precursor in the shallow ocean lineages from which the hadal organisms descended. This raises a question that has not yet been answered. Did these organisms develop these genes after they descended into the hadal zone, driven by the selection pressure of extreme depth? Or were some of these genes inherited from a much earlier lineage, one that originated in conditions even more extreme than the modern trench? One that may have been present in the deep ocean of an early Earth when conditions were uniformly more extreme than anything that exists today. The possibility that the genetic toolkit of hadal life contains echoes of the earliest biochemistry on this planet, the chemistry of the origin of life itself, is one of the most extraordinary ideas in modern biology. Not confirmed, not proven, but actively being investigated by researchers who have begun to understand that the deepest trenches are not just extreme environments. They may be the closest living connection we have to the conditions under which everything alive on this planet first learned to exist. There is one more dimension to the origin of life question that the hydrothermal vent hypothesis opens up, and it is perhaps the most unsettling. If life can begin in darkness, under pressure, driven by geochemical energy rather than sunlight, then the requirement for a sun becomes optional. Not just optional for the continuation of life, as the vent ecosystems have already demonstrated, optional for its beginning. If the first self-replicating chemistry can arise in a hydrothermal crack in an ocean floor, then any planet or moon with liquid water and geothermal activity is a candidate for life. Not just the ones in the narrow habitable zone around their star where liquid surface water is possible. Any world with an ocean kept liquid by tidal heating or radioactive decay. Any world with a cracked, geothermally active seafloor. Any world with the chemistry of rock and water and heat. The number of such worlds in the solar system alone, let alone the galaxy, is far larger than the number of worlds sitting comfortably in the habitable zone of a star. The hydrothermal vent origin hypothesis, if correct, does not merely change where we think life on Earth began. It expands the potential address book for life in the universe by orders of magnitude. And it points us directly at the places we should be looking next. Not at the planets orbiting other stars, decades of travel time away. At the moons in our own solar system. At the cold, dark oceans beneath their ice. At the vents that almost certainly exist on their seafloors. at the chemistry that may already be happening there, right now, in the same darkness and under the same pressures that first produced life here. Chapter 10. The Giants Below. Every few years, a new film or documentary series resurrects the same idea. Somewhere in the unexplored deep, something enormous is hiding. A creature large enough and ancient enough to have survived the extinction events that claimed its relatives, watching from the dark, undiscovered, possibly Megalodon. Megalodon was real. This is worth stating clearly, because the creature has accumulated so much fictional mythology that its actual existence sometimes gets obscured by the stories built around it. Otodus megalodon was a shark. It was genuinely enormous. Estimates based on the scaling of its fossilized teeth, some of which reach lengths of 17 centimeters, suggest a body length of somewhere between 15 and 20 meters. That is roughly 3 times the length of the largest great white sharks alive today. It had the largest bite force of any creature that has ever lived on this planet, as far as we currently know. It was the dominant apex predator of the world's oceans for millions of years, from approximately 23 million years ago until its extinction roughly 3.6 million years ago. And it cannot be alive today. Not in the trench, not anywhere. The argument for its survival always rests on the same foundation. We have not fully explored the deep ocean, therefore we cannot be certain what lives there. The logic sounds reasonable until you examine what Megalodon actually was. Megalodon was a warm-water coastal predator. It fed on large marine mammals, whales, sea cows, seals, animals of significant size and caloric density. An animal of Megalodon's mass would have required enormous and continuous caloric input to maintain its metabolism. The deep ocean is a food desert. The total biomass of large prey animals available at depth is a tiny fraction of what exists in productive coastal shallows. An animal of Megalodon's size could not survive on what the deep ocean offers. It would starve in weeks. Furthermore, Megalodon's teeth are extraordinarily durable, made of a highly mineralized enameloid that resists degradation for millions of years. We find Megalodon teeth in abundance in sediments from its known range and time period. They are scattered across ocean floors around the world. If Megalodon were alive today, or had been alive in the last few thousand years, we would be finding modern-dated teeth. Not just occasionally, constantly. We are not finding them. The fossil record is an absence of evidence that, in this case, genuinely is evidence of absence. The trench does not hide Megalodon. But the idea that the deep ocean hides genuine giants is not wrong. It is simply pointing at the wrong kind of giant. When scientists began lowering baited traps into the Mariana Trench to sample the fauna of the hadal zone, they expected to find strange organisms. The organisms they found were not all strange. Some were deeply familiar. Amphipods are among the most ubiquitous small crustaceans in the ocean. In the shallow world, they are the size of a fingernail. They are the sandhoppers you find on beaches, the freshwater scuds you might see in a stream. Common, unremarkable, measuring a centimeter or 2 at most. The amphipods that emerged from the Mariana Trench were 20 centimeters long. Alicella gigantea, the giant amphipod, is white and pale and translucent in the way of many hadal organisms. Its body plan is immediately recognizable as an amphipod. The same curved posture, the same arrangement of limbs, the same basic architecture you would see in a beach hopper, but scaled to something that looks not just unusual but genuinely wrong, an adult shoe in length. Multiple examples from other hadal trenches have reached 34 centimeters. They emerge from the bait traps in numbers, dozens at a time, swarming over the food source with an efficiency that makes clear they are not struggling at these depths, they are thriving. The phenomenon that produces this size increase is called deep-sea gigantism, and it is documented across multiple animal groups in the deep ocean. The leading explanations are still being debated. One involves metabolic rate. In the cold of the deep ocean, metabolic processes slow dramatically. One consequence of a very slow metabolism may be that the chemical signals that tell an organism to stop growing are delayed or diminished. In shallow water, an amphipod reaches adult size within months. At depth, with a metabolism running at a fraction of the normal rate, the same animal may continue growing for years or even decades, reaching sizes that have no shallow water equivalent. Another contributing factor may be the resource scarcity of the environment. In a food desert, a larger body provides an advantage. More fat reserves to draw on between meals. More energy stored to survive the months or years between major food events. Whatever the mechanism, the result is an animal that manages to be both deeply familiar and deeply unsettling. It is not alien. It is not a creature from a separate evolutionary tree. It is something you have seen, scaled past the point where familiarity provides comfort. And then there are the xenophyophores. On the floor of Challenger Deep, scattered across the pale silt in shapes that resemble sponges or brain-like lobes, researchers have found organisms that can reach the size of a dinner plate. Some have been measured at 20 centimeters across. They look complex. They look like colonial organisms, like structures built by many cells working together. They are not. Each individual organism, regardless of its size or its apparent complexity of form, is a single cell. Xenophyophores are the largest single-celled organisms on Earth, by a significant margin. Their bodies contain not one nucleus, but thousands, produced by repeated nuclear division without cell division. The cytoplasm that fills their enormous single-cell bodies is held in a lightweight, delicate framework they construct themselves. They collect particles from the surrounding sediment, sand grains, the empty shells of foraminifera, mineral flakes, and glue them together using a secretion from their own body into an intricate architectural structure called a test. The test gives them their shape and provides some mechanical support without requiring the energetically expensive process of building a calcified skeleton. A creature the size of a dinner plate, visible to the naked eye, complex in shape and behavior, that is nevertheless a single cell with no nervous system, no organs, and no intercellular communication. It is one of the most profound demonstrations that the rules of biology at the bottom of the world are not the rules we were taught at the surface. The xenophyophore also plays a role that extends beyond simply being remarkable. Because of their enormous surface area relative to their single-cell body, xenophyophores are believed to be important concentrators of certain trace metals and radioactive compounds in the sediment. They accumulate barium, lead, uranium, and thorium in their tissues at concentrations far above the surrounding environment. In areas of the seafloor where human activity has introduced contaminants, the xenophyophores' accumulating behavior means it becomes a living record of that contamination, a biological archive of what has settled on the hadal floor. Studying their chemistry tells us what the bottom of the world has absorbed from the surface world above. This accumulating property is shared, to varying degrees, by many hadal organisms. The amphipods that swarm the bait traps are not just scavengers. They are sampling everything that falls from above, digesting it, incorporating its chemistry into their own tissues. When researchers analyze the chemical content of hadal amphipods, they are reading a history of the surface world as recorded by the organisms at the bottom. The giants of the trench floor are not just biological curiosities. They are, in their patient and methodical way, keeping a record of everything we have sent down to them. And what that record currently shows is not encouraging. But that is a story for a later chapter. For now, the giants simply wait in their dark kingdom. Enormous, translucent, impossibly alive at the bottom of everything. Chapter 11. The Slow Kingdom. There is no light at the bottom of the Mariana Trench. There is no photosynthesis. There are no plants. There is no direct connection to the sun that powers almost every living system we have ever studied in the surface world. The hydrothermal vents, with their chemosynthetic ecosystems and their volcanic heat, exist only at scattered, rare points across the trench floor. For the vast majority of the hadal zone, thousands of square kilometers of cold, dark, featureless silt, neither sunlight nor geothermal heat provides direct energy. And yet, life is there, not sparse and barely detectable, present, functioning, sustained. On what? The answer falls from above, slowly, continuously, without interruption. For as long as the surface ocean has been productive, which is hundreds of millions of years, a rain of organic material, invisible to any eye and too light to feel, descends through the entire water column from the sunlit zone all the way to the deepest floor of the trench. Scientists call it marine snow. Marine snow is not a single substance, it is everything. Dead phytoplankton, the microscopic single-celled algae that form the foundation of the ocean food web, shed from the sunlit surface in countless trillions of particles every day. The fecal pellets of the animals that ate those algae, mucus secretions, fragments of dead bodies at every size from microscopic to massive, fish scales, shed exoskeletons from molting crustaceans, the compressed, partially digested remnants of everything that ever lived and died in the water column above. Each particle is small and light. A single particle of marine snow can take weeks to months to fall from the surface to the floor of the Mariana Trench. 11 kilometers is a long way to fall slowly. And on that journey, the particle passes through every zone of the water column, through every layer of the ocean's ecology, each populated by organisms that have evolved specifically to intercept and consume exactly this kind of falling material. By the time a particle of marine snow reaches the hadal floor, it has been eaten, partially digested, excreted, and eaten again multiple times. An estimated 90% or more of the organic material that leaves the surface ocean never reaches the abyssal floor, let alone the hadal depths. What arrives at Challenger Deep is not marine snow. It is the crumbs of the crumbs, the last residue of a feast that happened miles above and months or years ago. Life in the hadal zone is built on this residue. Every metabolism there, every cell division, every movement of every amphipod or sea cucumber or snailfish is powered ultimately by the decayed remnants of photosynthesis performed by microscopic algae at the surface of the Pacific Ocean. The connection exists, but it is attenuated to near nothing by the time it arrives, which is why the metabolisms of hadal organisms are almost unimaginably slow by surface standards. Cold slows chemical reactions, pressure alters them, and scarce fuel means that burning that fuel fast is not a viable strategy. Into this slow, sparse, patient economy comes, very occasionally, something that changes everything at once. A whale dies. Not often, not predictably, but when it does, and when the body is large enough and buoyant enough to sink rather than decompose and disperse at the surface, it falls. A 90-ton blue whale, the largest animal alive, drifting downward through the water column over the course of days, arriving eventually at the seafloor as something that no organism on the hadal floor has any equivalent for in their normal experience. 1 point on the barren mudflat receives, in a single event, more organic matter than it would accumulate under normal conditions in thousands of years. Scientists have studied whale falls in detail since the first deliberate observations in the 1980s, and what they have documented unfolds in 3 distinct stages, each lasting years to decades, each supporting a different community of life. In the first stage, which can last from months to several years depending on the size of the carcass, mobile scavengers arrive from the surrounding seafloor and water column. Sleeper sharks, attracted by chemical signals carried on the current, arrive first and begin consuming the soft tissue in efficient, rapid bursts. Hagfish, creatures that can tie themselves into a knot and use the leverage to tear chunks from a carcass, descend, and feed. Amphipods arrive in numbers that are almost difficult to comprehend, covering the whale in a living carpet, stripping tissue from bone with the collective efficiency of millions of small mouths. In weeks to months, the soft tissue is gone, the skeleton remains. In the second stage, opportunist organisms colonize the enriched sediment around the carcass. The decomposing organic material that has leached into the surrounding mud creates a zone of unusual biological richness. Polychaete worms, crabs, and bacterial mats bloom in the enriched sediment, drawing energy from the elevated organic content. This stage can last several years. The third stage is the one that produces the most extraordinary outcome. Chemosynthetic bacteria colonize the lipid-rich bones of the whale skeleton itself. The bones of a large whale contain enormous quantities of fat, oil stored in the porous bone structure, and as bacteria begin to break down that fat in the absence of oxygen deep within the bone, they produce hydrogen sulfide. That hydrogen sulfide drives a chemosynthetic ecosystem directly analogous to the one found at hydrothermal vents. Tube worms colonize the bone, mussels settle around it, clams. Species characteristic of hydrothermal vent communities, found nowhere else in the surrounding seafloor, appear at the whale fall as if the bones themselves were a vent. Zombie worms, the extraordinary ossidacs, bore directly into the bone and digest the fat within it through bacterial partners living in their tissues. A single large whale fall can sustain this complete, layered, chemosynthetic ecosystem for 50 to 100 years. One death in the light above creates a world in the dark below that outlasts most human relationships, most careers, most institutions. A world that exists because something enormous was alive and then was not, and fell downward through 11 kilometers of cold water to land on a floor that had been waiting in the dark for just such a gift. Patient as only geological things can be patient, ready as the deep always is to make something out of whatever the surface sends down. Beneath the whale fall, beneath the sediment, beneath even the remarkable organisms that have evolved to live on the hadal floor, there is one more layer to the economy of the abyss. One that makes even the whale fall ecosystem look bustling by comparison. When scientists began drilling into the sediment beneath the trench floor, not just scraping the surface, but penetrating meters down into the mud and into the rock itself, they found microbes living at depths and in conditions where almost nothing should survive, not living on marine snow, buried far below any organic fallout. In rock that had not seen the surface world for millions of years, these microbes appeared to be drawing energy directly from the rock itself. Stripping electrons from mineral compounds in the rock in a process so slow, it barely registers as metabolism by any standard we normally use. Some cells may divide once every few thousand years. Their entire existence operates on a timescale closer to geology than to biology. There is evidence, still being investigated, that some of these organisms may be powered partly by the natural radioactive decay of minerals in the rock around them. The low-level radiation released by isotopes in the rock splits water molecules, releasing hydrogen that can serve as an energy source for certain microbial metabolisms. It is the faintest possible trickle of energy, extracted from the slow disintegration of matter itself. But for a microbe that has slowed its existence to a near geological pace, it may be enough. These organisms, if the evidence holds, would be essentially independent of the surface world, not connected to the sun, not dependent on whale falls or marine snow or vent chemistry, living on deep time itself. A second, parallel biosphere beneath the floor of the abyss. An entirely separate experiment in life, running on its own rules, in its own darkness, for its own millions of years. The slow kingdom beneath the slow kingdom, patient beyond any measure that surface life has a word for. Chapter 12. Secrets in the Silt. The Mariana Trench was confirmed as the deepest place on Earth in 1875. Its extreme depth was precisely measured and documented by 1960, and for most of the decades that followed, it was treated by the public imagination as the ultimate expression of remoteness. A place so far below the surface, so physically defended by pressure and darkness, that nothing we did above could reach it. This assumption was wrong before it was ever fully formed. When James Cameron reached the floor of Challenger Deep in 2012 and found a plastic bag, it was not the beginning of the contamination story. It was a dramatic confirmation of something that had been happening for decades before any human being ever visited the bottom. The surface world had been sending itself downward long before it sent anyone to look. The contamination of the hadal zone takes several forms. Each one is distinct. Each one tells a different story about how a civilization interacts with the parts of the world it considers beyond its reach. The most pervasive and the most difficult to reverse is the microplastic contamination. Plastics entered mass production in the 1950s. From their earliest years of widespread use, plastic objects that reached the ocean surface began a slow journey downward. Not quickly. Plastic does not sink with any urgency. It degrades on the surface under ultraviolet radiation into smaller and smaller fragments, breaking apart over years and decades into pieces too small to see with the naked eye. These microplastic particles, some no larger than a few micrometers across, are then carried downward through the water column by the same processes that carry marine snow. They are ingested by organisms in the upper ocean, incorporated into fecal pellets, and sedimented steadily toward the floor. In 2018 and 2019, researchers published the results of sampling campaigns across multiple hadal trenches, including the Mariana. Their findings were unambiguous. Microplastic particles were present in every single sample collected from every single depth tested, not occasionally, without exception. The sediment of Challenger Deep contains microplastic fibers. The water column above it contains microplastic particles. The bodies of the amphipods living there contain microplastic fibers in their digestive tract. Organisms that have never been exposed to sunlight, living in a place that no human visited until 1960, are now carrying fragments of our consumer products inside their bodies as a routine feature of their biology. The geometry of the trench makes this worse than it would be in any other deep ocean environment. A flat, abyssal plain allows particles to disperse over wide areas. The trench is a concentrator. Its V-shaped geometry funnels particles toward the deepest point. Material that arrives anywhere in the broad upper reaches of the trench system is directed, by gravity and geometry, toward Challenger Deep. The deepest point on Earth is also the most efficient collector of everything that falls into it. The contamination is not spread thin across the trench floor. It concentrates at the bottom. Microplastics are not the only contaminants the trench has received. Persistent organic pollutants, a category that includes PCBs and brominated flame retardants, are synthetic chemicals that were manufactured in enormous quantities from the mid-20th century onward. They were used in electrical equipment, in fire-retardant coatings, in industrial processes. They were banned in most countries decades ago when their toxicity and environmental persistence became clear. But they do not break down. They accumulate in fatty tissue, and they follow the same route through the food web that everything else follows. From the surface to the water column to the sediment to the organisms, researchers who analyzed the tissue of amphipods from the Mariana Trench found PCB concentrations comparable to those found in the most heavily industrially polluted coastal areas of the northwestern Pacific. The Suruga Bay in Japan, one of the most contaminated marine environments in the world due to decades of industrial runoff, has amphipod PCB levels roughly similar to those found in the hadal organisms of the Mariana Trench. An animal living in a place so remote that human beings could not visit it until within living memory is carrying a chemical signature indistinguishable from an animal living in one of the most polluted harbors in Asia. There is also the matter of what was deliberately placed in the deep ocean. From the 1940s through the 1980s, multiple nations, including the United States, formerly used the deep ocean as a disposal site for radioactive waste. The reasoning was logical within the assumptions of the time. Seal the material in steel drums, encase the drums in concrete, lower them to the deepest accessible water. The depth would isolate the material. The pressure would keep the containers intact. The distance from human populations would render any eventual leakage harmless through dilution. Each part of this reasoning has since been shown to be flawed. No steel drum is designed to withstand indefinite exposure to saltwater corrosion combined with extreme hydrostatic pressure. The drums buckle, they corrode. Eventually they leak. And when a drum leaks in the hadal zone, the trench geometry that makes it the most remote place on Earth also makes it the worst possible location for a leak. There is no open plane to disperse the material across. There is only the concentrating funnel of the trench, directing everything toward the deepest silt, where it enters the sediment, is absorbed by the organisms living there, and begins its slow journey up the food web. International dumping of radioactive waste at sea was formally banned in 1993 under the London Protocol, but the material that was dumped before that ban is still there, still in the sediment, still in the water, still in the bodies of the organisms that call the trench home, and still, in some cases, leaking from containers that were built to last decades in an environment that will hold them for centuries. The trench is not a pristine wilderness. It has not been one for a long time. The plastic bag that Cameron's lights found on the floor of Challenger Deep was not a sign that something had gone wrong. It was a sign of how comprehensively and how long ago the contamination had arrived. The deepest place on Earth carries our fingerprints everywhere, in the sediment, in the water, in the tissue of every organism we have ever tested. The silt at the bottom of the world is not a blank record. It is a detailed and unflattering archive of everything the surface world has discarded. And it has been keeping that record patiently, in the dark, for longer than most of us would like to know. There is a Cold War dimension to this story that has never been fully resolved and, by its nature, may never be. The 1960s saw the first confirmed human descent to Challenger Deep, funded in part by the United States Navy. The Navy's interest in the trench was not purely scientific. The deep sound channel, which makes the trench one of the most powerful passive acoustic listening environments on Earth, was of obvious strategic interest during an era defined by the cat-and-mouse game of submarine detection. The Navy's SOSUS program, a classified global hydrophone network built to track Soviet submarines, exploited the properties of the deep sound channel across the Pacific. Whether listening arrays were ever installed within the trench itself, exploiting its extraordinary acoustic geometry, is classified. Whether they remain active today is classified. What sits in the silt beneath Challenger Deep, placed there by intelligence programs that operated in complete secrecy for decades, is something the public record does not say. The trench's depth is not only a physical fact. For at least one major government, it was a strategic asset, and strategic assets tend to accumulate their own kind of secrets. What the trench holds in its silt between the microplastics and the corroding drums and whatever the Cold War left behind is a record that future scientists may one day be able to read more completely than we can today. Every layer of sediment is a timestamp. Every chemical signature is an origin story. The trench is an archive, patient, comprehensive, entirely indifferent to whether we find what it has stored there, useful or shameful or both. Chapter 13. The Coming Gold Rush. The minerals we need most in the 21st century are becoming harder to find on land. Cobalt, which is essential for the batteries that power electric vehicles and portable electronics. Neodymium and dysprosium, rare earth elements required for the powerful permanent magnets inside electric motors and wind turbines. Copper and zinc in the concentrations needed to build the electrical infrastructure of a decarbonizing economy. Manganese, nickel, silver, Gold. The raw materials on which the green energy transition depends are not evenly distributed across the planet, and the places where they are concentrated are increasingly complicated, politically, environmentally, logistically. At the bottom of the ocean, however, they are sitting in extraordinary concentrations, doing nothing, in international waters, with no existing regulations strong enough to prevent them from being extracted. When the superheated fluid of a black smoke event hits cold seawater and its dissolved minerals precipitate, it does not simply create a momentary cloud. Over years and decades and centuries, those precipitating minerals accumulate into the hard mineral structures of the vent chimney itself. Polymetallic sulfide deposits. Solid rock formations built from layer upon layer of copper, zinc, iron, silver, and gold-bearing minerals, stacked up around the vent opening in structures that can reach the height of a 10-story building. At certain sites, these deposits contain ore grades, meaning concentrations of target minerals per ton of rock, that are significantly higher than the ore grades that justify mining operations on land. Beyond the sulfide deposits around active vents, the abyssal plains and trench slopes also host two other categories of mineral accumulation. Polymetallic nodules, potato-sized lumps of manganese, nickel, cobalt, and copper that form extremely slowly on the sediment surface over millions of years, and cobalt-rich ferromanganese crusts that develop on the flanks of seamounts and ridges, sometimes reaching thicknesses of 10 centimeters or more, with cobalt concentrations that make land-based sources look impoverished by comparison. The combination of resource scarcity on land and resource abundance in the deep ocean has triggered what industry insiders and marine scientists alike are calling a new gold rush. Not metaphorically, literally. Dozens of countries and private corporations have filed exploration licenses with the International Seabed Authority, the body established under the United Nations Convention on the Law of the Sea to govern the resources of international seabed areas. Companies from Canada, Japan, China, South Korea, Germany, and elsewhere have invested in the development of robotic mining systems designed to operate at depths of 1 to 5 kilometers. Machines the size of small buildings. Submersible grinding systems designed to break polymetallic nodules from the seafloor and pump the resulting slurry to processing ships on the surface through hoses kilometers long. As of the early 2020s, commercial deep-sea mining had not yet begun on a large scale, but the regulatory framework that would allow it was actively being written. The International Seabed Authority was engaged in the process of finalizing the mining code, a set of rules governing how extraction of seabed minerals in international waters would be permitted, monitored, and taxed. The mining industry was lobbying for the code to be finalized quickly. Environmental scientists were arguing that it was being finalized without adequate understanding of the ecosystems that would be affected. The problem with mining hydrothermal vent deposits is not simply that it would disturb the seafloor, it would destroy communities of organisms found nowhere else on Earth. Each hydrothermal vent system is a biological island, an isolated oasis of heat and chemistry in the cold, nutrient-poor desert of the deep seafloor. The tube worms, the endemic crab species, the specialized shrimp communities, the chemosynthetic bacterial mats that power the entire ecosystem are found at that vent and potentially nowhere else. Not in reduced numbers, not in degraded form, nowhere at all outside the precise chemical and thermal environment of that specific vent system. When scientists survey different vent fields, even within the same ocean basin, they regularly find species that are unique to one location. Species that evolved in the particular conditions of a single vent community and exist in no catalogue of life compiled from anywhere else on the planet. A mining operation targeting a vent deposit would not disturb this ecosystem. It would end it. The grinding machinery would destroy the physical structures in minutes that took thousands of years to build. The thermal and chemical gradients that the organisms depend on would be obliterated. and the enormous plumes of fine sediment generated by the grinding process would drift with the deep current for hundreds of kilometers, settling on and smothering neighboring communities that were never the target of the mining operation at all. The Mariana Trench itself was designated a Marine National Monument by the United States government in 2009. Commercial fishing is prohibited. Resource extraction is banned within the monument boundaries. These are meaningful protections. They are not complete ones. The monument boundaries do not extend into the surrounding international waters where the richest mineral deposits may lie. A mining operation just outside the legal boundary would generate sediment plumes with no respect for the line drawn on a map. Physics does not recognize maritime boundaries. Plumes drift where currents carry them. If they carry them into the monument, the protected ecosystem suffers the consequences of an operation that legally never touched it. The enforcement problem is equally fundamental. How do you police an area 7 miles underwater in permanent darkness in the middle of the Pacific Ocean? The answer is that you largely cannot. A robotic harvesting operation in international waters near the trench would be extraordinarily difficult to detect, document, and prosecute. The combination of legal ambiguity, physical inaccessibility, and the scale of the financial incentives involved creates conditions that environmental scientists find deeply concerning. We are at the beginning of a decision about what the deep ocean is for, whether it is a resource to be extracted when the economics justify it, or whether it is something else. A repository of biological diversity we do not yet understand, a record of the planet's history, a laboratory for processes that produced life itself. The decision is not purely scientific. It is a question about what kind of civilization we want to be in the places where no one is watching, where the darkness is absolute, and where the consequences of what we do next will play out over timescales long enough to outlast any government or corporation making the choice today. The urgency of that decision is also being shaped by geopolitics in ways that complicate the already difficult conversation between industry and conservation. The minerals concentrated in deep-sea deposits are also the minerals that underpin technological sovereignty in the 21st century. A country that controls rare earth element supply controls a critical choke point in the production of electric vehicles, advanced weapons systems, and consumer electronics. Several of the nations most aggressively pursuing deep-sea mining licenses are doing so not simply for commercial profit, but for strategic reasons. The seabed has become a theater of the same competition that plays out in trade policy and technology development, which means the decisions about deep-sea mining are not being made only by environmentalists and mining companies. They are being made in the context of a much larger contest about which nations will control the material foundations of the next century. The organisms at the bottom of the Mariana Trench did not evolve in the context of any of these human concerns. The tube worms growing around the vents were not consulted about the mining code. The xenophyrophores on the floor of Challenger Deep have no position on trade policy. The snailfish navigating the Hadal Dark do not know that their ecosystem has become a geopolitical asset. They simply exist, doing what they have been doing for millions of years, in the dark, in the pressure, in the extraordinary, patient, fragile silence of the deepest place on Earth. The question is not whether we have the technology to reach these minerals. We nearly do. The question is whether the fact that we can reach them is sufficient reason to do so, and whether the world we would be building with the materials we extract from the deep is worth the world we would be destroying to extract them. These are not questions with easy answers. They are questions that the coming decade will force every nation with an interest in the seabed to answer, in policy rooms and boardrooms and international negotiating chambers, mostly out of sight and mostly without the deep ocean having any voice in the proceedings at all. Chapter 14. The Last Unknown. There are 2 moons in our solar system that may harbor life. The first is Europa, one of the 4 large moons of Jupiter. Europa is covered entirely by a shell of ice that extends for tens of kilometers above a global ocean of liquid water. The surface is cold beyond anything that exists on Earth. Bombarded by radiation from Jupiter's enormous magnetic field. Visually, it is a cracked, streaked ball of white and brown ice, barren in every direction as far as any instrument has ever seen. No atmosphere to speak of, no warmth from the distant sun, no photosynthesis, no surface life of any kind. But beneath that ice, kept liquid by the tidal flexing of Jupiter's enormous gravity pulling and squeezing the Moon's interior, there is an ocean. An ocean that may be 2 to 3 times the total volume of all of Earth's oceans combined. Dark, cold, pressurized. And if the models are correct, heated from below by geochemical activity on the rocky seafloor at the bottom of that enormous body of water. The second moon is Enceladus, one of the moons of Saturn, smaller than Europa, but geologically more obviously active. In 2005, the Cassini spacecraft detected plumes of water vapor and ice crystals erupting from cracks near the south pole of Enceladus, jetting directly into space. Analysis of those plumes revealed the presence of water, organic compounds, silica particles that form only in high-temperature hydrothermal systems, and molecular hydrogen. The molecular hydrogen is the key detail. It is a direct indicator of ongoing hydrothermal reactions between liquid water and hot rock. The chemical signature of a black smoke event, expressed in material erupting from the surface of a moon 600 million miles from Earth. Enceladus has a hydrothermal system. It almost certainly has an ocean. And somewhere on the floor of that ocean, in the dark and the pressure and the heat of a geothermal vent, the same chemistry is taking place that takes place at the Mariana Trench system right now. If we want to understand whether life could exist on Europa or Enceladus, there is exactly one place on Earth to look for the answer. Not a laboratory, not a computer model. A real, functioning ecosystem running on exactly the energy source, in exactly the physical conditions that we expect to find on those moons. The Mariana Trench. Its hydrothermal vent communities are the only working model of life without sunlight that we have ever directly observed. Every organism that thrives there is evidence that the conditions on Europa and Enceladus are not prohibitive. Every biochemical adaptation of those organisms, every piezolite and flexible membrane and chemosynthetic pathway is a potential blueprint for what life on another world might look like. When we eventually send probes to those moons, as missions currently in development plan to do within the coming decades, we will be looking for exactly the kind of life the trench has already shown us. The probes will need to recognize the chemical signatures of chemosynthesis in water samples. They will need to detect the biological markers of pressure-adapted organisms in sediment. They will need to find the thermal and chemical gradients that indicate an active vent. Every piece of science we develop to study the hadal zone is science that directly enables the search for life beyond Earth. The trench is not only an extreme environment to be catalogued, it is our training ground for the search that may define the next century of human civilization. The way we will eventually explore it fully is changing. The era of the manned descent, the extraordinary moments of Piccard and Walsh, of Cameron, of Vescovo, may be giving way to something more comprehensive. The next generation of hadal exploration is robotic. Not the single large tethered vehicle of the 1980s and 90s, trailing a cable to a surface ship and limited to whatever the cable allowed. The future is autonomous. Multiple small AI-driven submersibles launched simultaneously from a surface vessel, communicating with each other through pulses of light and sound, navigating independently, mapping collaboratively, each one gathering data and returning it to the swarm. When one is lost, as some will be, the others adapt. When one finds a vent, it signals the group and they converge. The whole system is designed to lose individual components without losing momentum or purpose. Several of the most promising designs for these swarm vehicles are soft-bodied. inspired not by the engineering of steel spheres, but by the biology of the creatures that already live at depth. Bodies that flex with the pressure rather than resist it. Locomotion based on the jet propulsion of squids or the undulation of eels rather than rigid propellers. Materials that behave more like tissue than like metal. The most successful designs for hadal exploration may end up looking less like submarines and more like the organisms the trench already contains. Built, as those organisms are built, to work with the pressure rather than against it. This is also, in all likelihood, how we will explore Europa when the time comes. A lander will descend to the surface of the ice. A drill or melting probe will penetrate downward through the ice shell, which may be tens of kilometers thick, taking weeks to reach the ocean below. And when it arrives at the ocean interface, it will release a swarm, small, autonomous, soft, guided by the lessons learned in the darkest water on our own planet. But all of this, the robotic swarms and the Europa probes and the mineral debates and the contamination data, circles back to something that may be the most important truth the Mariana Trench holds. Not a scientific truth, a philosophical one. We live in an age that has declared the puzzle solved. Every satellite image and deep web archive and index database gives the impression that the knowable world has been known, that the map is complete, that nothing fundamental remains to be discovered. This is a comfortable belief. It is also a quietly impoverishing one. A world without genuine mystery is a world with a ceiling on its curiosity. And curiosity is the engine of science, of art, of philosophy, of the restless forward movement of civilization. The Mariana Trench is the physical proof that the puzzle is not solved. The phantom fish of Piccard and Walsh, still unresolved after 60 years. The Western Pacific Biotwang, still unexplained. The shadow biosphere in the deepest sediment, still theoretical. The full census of hadal species, still decades from completion. The contents of the classified archives in the Cold War silt, still sealed. The trench does not yield its secrets on a human schedule. It operates on geological time. It does not know we are curious about it. It does not know we exist. It has never required our attention, and it does not require it now. It simply is, ancient and indifferent and complete in a way that nothing we build or name or study can quite touch. That is not a discouraging thought. It is a gift. A world that still contains a place this deep, this old, this genuinely unknown, is a world that still has room for wonder. The map is not complete. The puzzle is not solved. And in the cold and the dark and the unimaginable pressure of the deepest place on Earth, something extraordinary is alive, patient, adapted, utterly at home. We were never meant to go there, and yet we went. And what we found, in the moments when the lights were on and the instruments were recording and the water pressed inward from every direction with its full and indifferent weight, was not an answer. It was a deeper question, the best kind, the kind that will take a very long time to resolve, the kind that, if we are careful, we will never quite finish asking. The lights go out now, the darkness returns, and the trench continues, as it always has, dreaming its slow, cold geological dreams in the permanent night at the bottom of the world. Thank you for spending this night with Earth at Night. If this journey moved you, or surprised you, or left you with something to think about as you drift towards sleep, please take a moment to like the video and leave a comment. Tell us what stayed with you. Tell us what you want to explore next. The community you build in the comments is what makes these journeys worth taking. Sleep well.